So my name is Subir Sarkar, and I'm the head of the particle theory group at the University of Oxford in the Rudolf Pyle Center for Theoretical Physics. But in fact, I don't just work in theory. I also work on a couple of experiments. Once at the South Pole, it's called IceCube. It detects high-energy neutrinos from outer space. And another one is called the Cherenkov Telescope Array, which looks for high-energy gamma rays. But essentially, I'm at the interface between theory and experiment. And my main interest is in what we call phenomenology. In other words, understanding in terms of fundamental laws what we see around us.
And so you've done work on the supernova.
That's right. So I'm not an astronomer, but the supernova data has been now made public, and our contribution was to analyze the data in a statistically rigorous way, which we believe it has not been done in the past. The point is that the supernovae are objects which are just like all astronomical objects. They're not all identical. So in fundamental physics, we are used to the idea that every electron in the world is identical. In fact, John Wheeler famously said it's the same electron everywhere. Okay, but supernovae are not quite the same. However, they are similar enough to each other that they are used as what's called standard candles. They put out the same amount of energy. Actually, in practice, they are so-called standardizable candles. You can make corrections based on how long they last and what color they look to try to reduce them to the same standard object. And then you can ask how faint are they looking, and then you measure the redshift of the galaxy they are embedded in. So that gives you a measure of the distance, and then from that you can try to work out if the expansion rate of the universe is slowing down or speeding up or staying the same. And there was a major discovery in the late 1990s that apparently, according to the supernovae, the expansion is speeding up. So in practice, what they actually measure is that the distant supernovae are about 30% further away than you would have expected them to be had the universe been slowing down. So that, of course, raises immediately lots of questions. When you say that 30% further away than you expected them to be, what if the supernovae had just become 30% less bright, right? That's always a worry. And so the whole game is one of trying to identify and pin down these systematic uncertainties. And that's where I thought the subject was until we actually looked at the data, which was made public in 2016. And then we discovered that the statistical analysis had actually allowed for the possibility of uncertainties in each measurement, and they then tried to fit the model of the accelerating universe to the data. So the point is that if you allow the uncertainty on each measurement to be arbitrarily large, then you can fit any model, and indeed they did. But if you adopt a more, the correct word for it would be a more, not so much honest, as a more rigorous way of statistical analysis called the maximum likelihood method, then it turns out that the evidence is not really that strong. And very recently, we have discovered that this apparent acceleration is not the same in every direction. It seems to be highest in the direction in which we are already, we know we are moving through the cosmic microwave background. So that's what makes us think that this is not really the effect of dark energy at all. It's simply an artifact of our being located in what is technically called a bulk flow. Our galaxy and neighboring galaxies are all coherently moving in one direction at several hundred kilometers a second. This is not the Hubble expansion, this is a deviation from the Hubble expansion. We don't know why it's doing that. It could be a big lump of matter nearby pulling us. Be that as it may, the fact that we are in this bulk flow means that we are not what we thought we were, Copernican observers. We are not typical observers. We are very special observers. And I think that dark energy is an artifact of our not taking account of this fact that we are not typical.
Why does that make us special observers?
Special only in the sense that we are not what the theory assumes we are. There's nothing fundamentally special about it. It's just like, I'm sitting at this particular spot on this particular river bank. I could be sitting at some other spot. There's nothing special about the spot per se, but depending on which spot I pick, I'll see the river differently.
And does this mean that if the evidence is flawed, that there's more experiments you can do in that to collect the evidence which isn't as flawed? Or why does it lead you to say that it's not dark energy, that it's the flow?
Because the only direct evidence for dark energy is the fact that it is supposed to be causing this accelerating expansion. So let me say that there is a way in which we'll find out, well, quite soon, within 20-30 years, because if the universe expansion is actually accelerating, then what we should do is measure the velocity of expansion today and then 10 years from now, right? That's what we call acceleration, right? And so far, all the measurements we have been talking about are made at one point in time. But quite soon, with a new telescope called the Extremely Large Telescope, ELT, it's being constructed right now in Chile, it will be possible to do what we call real-time cosmology. So you can actually monitor the redshift of an object and see it changing in time. And over a period of 10 years, it will change by about 1 part in 10 to the 9. But it's sufficiently sensitive, the instrument, that it can measure that. So this is called the redshift drift, and people had thought of this quite a long time ago, but they thought it would never be possible to measure it. And now with current technology we can. So we'll know eventually if the expansion rate is actually accelerating. But meanwhile, apart from the supernovae, people have found other ways to look for dark energy, but they're all indirect. They don't directly measure the effects of dark energy. They effectively measure the other components of the universe apart from dark energy, such as how much matter it contains, such as how much space-like sections are curved and so on. And then within the theoretical model, there is a connection between the things that you measure and the dark energy part, the cosmological constant, which you don't, and you infer that in the context of the model. But that inference is only as good as the model is correct. So if the model which was formulated 100 years ago, is not the last word, for example, the model assumes that the universe is totally homogeneous, smooth, and every direction is the same. But in our real universe, the universe is very lumpy, and it turns out that all directions are not the same. Whether this really has cosmological significance or not is still under study. This is not, what I'm talking about is not broadly accepted by any means by the majority of cosmologists. But we do feel we are onto something, because what we are doing is entirely data driven. There's no theory in it at all. We are just asking a very simple question: is the universe isotropic? Is the universe homogeneous? What effect would that have on us? We are at a particular position in this network, this so-called cosmic web of galaxies. Depending on the direction you look at, might we infer a different thing than if I looked in the opposite direction? So these questions have never been asked because the assumption has been that all directions are equivalent. But our real life experience tells us that usually that is not the case, and you can draw the wrong inference if you believe in a degree of symmetry which the real world does not reflect.
So do you believe it should be data-driven rather than sort of grand theories such as supersymmetry or blue sky thinking?
Oh, absolutely, because the theory here was actually that has failed miserably, because that's what I talked about in the debate earlier, this Einstein's cosmological constant. He recognized that the equation has a certain underlying mathematical structure that allows you to add a term called the cosmological constant to the equations. He added it for the wrong reason. He thought you needed to make the universe static, and now we know that actually it need not be so, and most of the time the universe could be expanding or contracting. But that is not actually a failure on his part at all. He recognized that the term had to be there, and it is not really Einstein's choice whether the constant has to be is there or not. So this famous story about how he said it was his greatest mistake, that has never been documented, by the way. It was George Gamow, who was famous for telling fibs, making up stories, who claimed that Einstein had said that in a letter to him. But Einstein, none of his notebooks actually show that he had ever said this. Anyway, the point is that that term is there, and that term we understand today in the modern understanding of physics, which is quantum field theory. It corresponds to the energy density of the vacuum. And the basic problem is that the energy density of the vacuum, if it couples to gravity in the way that Einstein thought of, would essentially have ever prevented our universe becoming the way it is today. So we don't understand that. This is the cosmological constant problem. You know, Steven Weinberg, who is one of the best known particle theorists there is, he said it is the bone in our throat. I think that really perfectly summarizes just what a big problem it is. Nobody has been able to solve it, and then after many years of trying to ignore it, because it affects nothing in the laboratory, you can do your experiments at the LHC and elsewhere, the cosmological constant has no effect there. So you can afford to ignore it, but not in cosmology. That's the only place where it rears its head again. And now astronomers claim they have found a value for it, which is non-zero. That raises another problem. Why is it important only today? You know, because the value of the constant is very, very small. It's of order the other energy densities today. And the other energy densities would have been bigger in the past. So there is a why now question. So lots of people are happily employed in trying to write papers, trying to address these questions. I think that no progress will be made on that because it's a very, very fine-tuned problem. But it has forced, I think, fundamental theorists to look at this unsolved issue, and I don't think I'm clever enough to ever solve it, but I'm in good company. Nobody else in the world has been able to do it either. But I think this is really the kind of challenge that today's generation of physicists should look forward to, that there is something really, really major and important for them to tackle that everyone else before them has failed to solve. And just playing games with it, calling it dark energy, quintessence, whatever, I think is just completely and utterly pointless. So that is just going to go away when we do better experiments and discover that the expansion is not really accelerating. I think we will discover that the cosmological constant is in fact as close to zero as we can measure it. That will bring back the old cosmological constant problem, which was bad enough, serious enough. So, this is a win-win situation.